Welcome to The Explainer. Today, we're going to dive into something really cool, how engineers and scientists create mathematical models of the world around us. It's a process called system identification, and we're going to break it all down.
Now, this whole explainer was put together by Dr. Nima Median, and it really takes us on a fascinating journey. We're going to build a model from the absolute ground up, starting with a perfect, ideal concept, and then slowly adding layers of reality until we have something that can truly describe how complex systems actually work.
So, everything kicks off with this fundamental challenge you see right here. On the left, we have a perfect, clean signal that we send into some kind of system, a black box, that we don't understand yet. But what we measure on the other side is, well, it's messy, and it's corrupted by noise. Our entire mission is to figure out what's happening inside that box to turn that neat input into the messy reality we actually observe.
So how are we going to crack this? Well, we've got a roadmap. First, we're going to build the ideal, perfect version of the system. Then, we'll introduce the messy complexities of the real world. After that, we'll learn how to actually describe all that random noise. And finally, we'll put it all together into one powerful, unified model. Let's get started.
Okay, let's jump right into section 1. Before we can even think about dealing with the messiness of the real world, we have to build our perfect foundation. We need to define the ideal system, the mathematical core that describes how a system should behave in a perfect world.
So we start with an ideal system, one that plays by three very simple, very predictable rules. First, it's linear. That just means if you double the input, you double the output. No surprises. Second, it's time-invariant, meaning it works the same way today as it will tomorrow. Its behavior doesn't change. And third, it's causal. It can only react to things that have already happened, not the future. These three rules give us our predictable starting point.
Okay, so we have this ideal box, but how do we know what's inside? How do we figure out its unique personality? We do it by finding its fingerprint, something called the impulse response. Think of it like this. You give the system a quick, sharp tap, an impulse, and then you just watch how it rings out and settles down over time. That response is like the system's DNA. It tells you everything you need to know about its fundamental character.
And this leads to a really, really crucial idea. The output you see from a system isn't just a reaction to what's happening right now. It's actually a mix of the current input and all the lingering echoes of past inputs. This mathematical mixing is called convolution. That equation you see perfectly describes how the system's memory, its impulse response, blends together with the entire history of the input to create the final output.
All right, let's move on. Section 2 is where things get really interesting. This is where our perfect, clean model smacks right into the messy, unpredictable real world.
So the first dose of reality? Computers. You see, our math is all smooth and continuous, but computers don't work that way. They can't see a smooth wave. Instead, they take little snapshots at discrete moments in time. This process is called sampling, and it's what turns our elegant theory into a series of data points that a computer can actually work with.
And this is the big moment. You see that new letter that just popped into our equation? That V of t? That's the real world crashing the party. It represents all the unpredictable, uncontrollable forces that corrupt our measurement. We lump all of that mess together and call it a disturbance. And just like that, our model isn't so perfect anymore.
Now, these disturbances aren't just some vague idea. They come from very real places. It could be tiny errors from the sensors themselves. We call that measurement noise. It could be external factors we can't control, like a sudden gust of wind nudging a drone off course. Or it could even be random fluctuations from inside the system itself, which we call process noise.
Okay, so we've admitted that our system is messy, but we can't just throw our hands up and say, oh, well. The next step, and this is where the genius comes in, is to actually model that mess. We're going to give this randomness a story and a structure.
We start with the most basic building block of randomness you can imagine, white noise. Just look at the graph on the left. It's pure chaos, right? It looks just like static on an old TV. And on the right, you can see its power spectrum. It's totally flat. That means it has no favorite frequency, no pattern, and absolutely zero memory. It is the definition of pure, unpredictable randomness.
But here's the thing. Most noise in the real world isn't pure static. Things like wind gusts or traffic noise have some kind of structure to them. So what do? Well, the idea is beautifully simple. We take that pure random white noise and we pass it through a filter. What comes out the other side is what we call colored noise, a much more realistic model for the kind of disturbances we see in the real world.
And this slide right here is the proof in the pudding. We're looking at something called autocorrelation. You can think of it as a signal's memory of itself. On the left, for white noise, you see that single spike right at 0? That means it has no memory whatsoever. A value is only correlated with itself at that exact instant. But now look at the colored noise on the right. See that decaying curve? That shows a clear connection to its past. Its history absolutely influences its present.
All right, we are almost there. We have a model for our system, and we have a model for the noise, but trying to work with them together is still, well, it's a bit of a headache mathematically. Let's find a much smarter, more elegant way to put it all together.
So here's the big question we're facing. Our model is technically complete, which is great, but we're stuck working with these infinite sums, these convolutions. They're clunky and they're difficult to work with. There's got to be a better way, right? Is it possible to somehow turn all this complicated math into something as simple as multiplication?
And the answer is a resounding yes. The solution is something called the transfer function. By jumping from the familiar time domain into a new mathematical playground called the z-domain, we can perform a kind of magic trick. That nasty, complicated operation of convolution, it just becomes simple multiplication. This is an absolute game changer for analyzing systems.
And here it is. This is what it has all been leading to. By using that same transfer function logic for both our system, that's the G, and for our structured noise, that's the H, we get this one single beautiful equation. This right here is the cornerstone of modern system identification. It elegantly captures everything we've talked about.
So let's just take a breath and recap the journey we just took. We started with an ideal, perfect core. Then we introduced reality by acknowledging all the disturbances. We figured out how to characterize that noise by modeling it as filtered white noise. And finally, we combined everything into one unified, elegant model that's ready to go. And that's not just a cool piece of math on a slide. This model is the foundation for everything from tuning the autopilot in an aircraft to optimizing a chemical plant to predicting financial markets. It gives us an incredibly powerful tool to understand the world. Which really just leaves us with one final thought. Now that you know how to describe almost any black box with one elegant equation, what mystery in your world would you want to model first?